Hi, my name is Andrew Betz, and this is my final presentation for Advanced Mechatronics at the City College of New York. Here's an overview of what I'm going to be presenting about today. What is a powered exoskeleton? You can see a view of the City College exoskeleton on the right. This is the hip exoskeleton. Powered exoskeleton is a wearable device that is used to enhance human motion, especially for the limbs or spine, and it often has an external power source. This is a model for the mathematical derivation of the governing equations for the hip exoskeleton. Now I'm going to talk about backdrivability, which is essentially a measure of how much the output axis can affect the input axis. What does it mean for an exoskeleton? So if you have high backdrivability, that means the exoskeleton is going to be compliant to the user, so the user can overpower the skeleton without being hindered too much. Low backdrivability means the exoskeleton is going to fight the user's motion, so it's essentially going to act like a cage. How do we calculate the backdrivability of an exoskeleton? Well, to measure backdrivability, we look at the resistive torque produced when a human walks while the exoskeleton is not powered. A higher resistive torque implies a lower backdrivability. So the first thing we need is a transfer function for the applied torque per the human angle. So you have your voltage 0, then you have your electrical component transfer function. I'm going to be using block diagrams from Simulink, which is a plugin for MATLAB. These blocks just represent saturation points for the hardware that we're actually going to be using. And then you have to look at your torque constant block. Now I'm going to look at the dynamic motion transfer function. And in Simulink, it's going to look like that. And then for the for the back torque from the friction, you're going to get a model that looks like that. Now you realize that the angle 1 was the same as the motor, and then you have to know that the gear ratio is going to affect angle 2. Next, you look at the transmission torque, which is calculated this way, and this is what it's going to look like in Simulink. Okay, to solve this transfer function, I use a symbolic editor in MATLAB, and it spits out this transfer function, but because the inductance is many orders of magnitude smaller than the other terms, such as the resistors, they can be neglected, and you get this much more elegant transfer function. This is what the whole thing looks like when you put it together. You might be wondering what this thing is. Well, it's a chirp function. It's a way that we can oscillate the input while also cranking up the frequency. This is just 5 degrees in radians. This is the output data to the workspace. And this is just to see a quick graph of what you have. Now I'm going to talk about bandwidth. Bandwidth is a metric to characterize how fast a system can react to an input. It's measured in hertz. So what does it mean for the exoskeleton? A high bandwidth exoskeleton is going to be desired because the system can adjust itself many times per second. Low bandwidth exoskeleton could be detrimental because you're essentially going to introduce a lag into the system. So how to calculate bandwidth in an exoskeleton? Well, to calculate bandwidth in an exoskeleton, you fix the human input and compare the ratio of output signal for input signal for a given reference torque. So control algorithms are going to affect the bandwidth, so they're included in the model. And a typical bandwidth is a frequency where the output over the input drops below -3 decibels, which is around 70.7%. To calculate this, we need a different transfer function, which is the applied torque divided by the reference torque. So equations 2 through 8 can be reused. Equation 1 is going to be modified for the PID controller. Simulink, it's going to look like that. We have a nice package that show your PID constants, and then your theta H is going to be fixed to 0. I once again solved this with MATLAB symbolic solution kit. It spits out this very ugly transfer function, and then I try to play around with the algebra to make it more beautiful. And this is the best that I did, and you get a much cleaner looking transfer function. This is what the block diagram looks like at the end. Now our chirp function is for your reference torque. And there's no theta H because I'd just be subtracting 0 since I fixed theta H to 0. And this is just a little data log section. We can use this to help pick the best actuator to work with the human body. Actuator is going to control the motion. And our actuator is going to be the motor and the transmission system. So you have your conventional actuators, which have a low torque motor, a high gear ratio, and a stiff sensor. Your series elastic actuator replaces that stiff sensor with your spring encoder. And then you have this new guy, a quasi-direct drive, who has a high torque density motor and a low gear ratio. So you can see the weights are different for each of these systems, but we still need to know what we really care about, which is the compliance with the backdrivability and the bandwidth. So the reason why conventional actuators aren't good for exoskeletons is because their backdrivability is so low. So we're going to run a simulation based on some actuators, and we're going to be using PD control when it comes to that bandwidth calculation. The coefficients are in the top left corner. So the backdrivability simulation, we saw that our series elastic actuator had 14.8 newton meters, our quasi-direct drive had 2 newton meters, and this means that quasi-direct drive is more backdrivable than the series elastic actuator. For a bandwidth simulation, you see that the SEA bandwidth was around 16 hertz for 1 newton meter, and the quasi-direct drive was around 220 hertz for 1 newton meter. So the quasi-direct drive has a higher bandwidth than the SEA. Going back to our table, if we're going to fill in the results, you see that your series elastic actuator, it's better than a conventional actuator, but the quasi-direct drive looks like it's going to be the future for robotics. So what I learned in this project, well, I learned about metrics that are important to exoskeleton design, which include backdrivability and bandwidth. I learned how to use Simulink modeling because I had to model the hip exoskeleton in Simulink. I learned about control theory for the PID controller. And I also learned about state-of-the-art actuators in the robotic field, which is quasi-direct drive. I want to thank my professors and TA for a great semester. Take care.